Hello all, welcome you to this new chapter, that is Kinetic Theory of Gases. In short, we can call it as KTG. So this is the lecture 1 of KTG and this is the simple chapter available in the +1. Okay, both in competitive examination point of view as well as board examination point of view. This is basically very simple. Okay, and most of the concepts in this chapter is already familiar to you in chemistry, alright? Just like gas laws, Boyle's law, Charles' law, also what is mean by ideal gas, what is mean by real gas, you know all these things, alright? So, let's see which all are the content that we have to learn in this chapter, okay? So, the topics are, we will learn behavior of gases, then gas laws, kinetic theory of ideal gas, different speed of gas molecules, Maxwell-Boltzmann distribution curve, then pressure of an ideal gas, kinetic interpretation of temperature, then degree of freedom, law of equipartition of energy, then specific heat capacities of gases, then we will learn that of water as well as solids, then last we will learn about mean free path. Okay, so this chapter, that is kinetic theory, is basically dealing with the behavior of gas, right? It is based on some properties like volume, temperature, pressure of the gas. It was developed by Maxwell, Boltzmann and many other persons. Okay, so as I have already told you, this is a chapter you don't have to worry because all the concepts in this chapter is very easy. Okay. So first, let's move on to behavior of gases. Okay, all gases under low pressure and high temperature satisfy a relation between their state variables like pressure, temperature and volume, right? What is that relation? Yes, obviously you are thinking PV is equal to nRT, right? But I am writing it as PV is equal to NKBT. Okay, PV is equal to NKBT, where P is the pressure, V is volume, capital N, okay, that is number of molecules, okay, number of molecules, KB, that is Boltzmann constant, right? Boltzmann constant, okay, Boltzmann constant. What is the value? Yes, the value is 1.38 into 10 raised to minus 23 Joule per Kelvin. Okay, so that is the value of Boltzmann constant and T will be your temperature. Okay, you know that your number of moles, that is mu, okay, either you can represent number of moles as mu or small letter n. Okay, I am here using mu. Okay, so number of moles is nothing but number of molecules divided by Avogadro number, right? That is Na. Okay, Na is Avogadro number. Avogadro number. What is the value? 6.023 into 10 raised to 23. Right? That is Avogadro number. From here, you can write that your number of molecules will be equal to number of moles into Na. Alright? So, the first one can be called as equation number 1 and this can be called as equation number 2. Okay. Now, you put 2 in 1. Okay. So that your PV will be equal to mu mu Na into kBt, right? Instead of this n, you are substituting this second one. Okay, so that will become mu Na into kBt. Alright? In this, Na into kB. What is Na into kB? Yes, it is capital letter R. Right? What is it called as? Universal gas constant. Right? So this is called as universal gas constant. Alright, universal gas constant. Okay, what is the value of R? You have learned that based on the unit system we are following, okay, there are many values for R. According to SI unit, the value of R will be 8.314 joule per mole Kelvin. Okay, therefore you can write this equation as PV is equal to mu RT. PV is equal to mu RT. What is this equation called as? This equation, PV is equal to mu RT, is called as ideal gas equation. Right? You are very familiar with it. Ideal gas equation. Okay, ideal gas equation. What is mean by ideal gas? Ideal gas means those gas which obey ideal gas equation, that is PV is equal to mu RT under all condition of temperature and pressure. Okay, such gases are called as ideal gas. Then let me ask you something. What is the name for gases that does not obey ideal gas equation under all condition of temperature and pressure? Think of it. Yes, some of you may tell non-ideal, right? Non-ideal gas. Okay, they are basically called as real gases. So, real gas does not obey ideal gas equation under all condition of temperature and pressure. So, before learning the graph related to the behavior of different gases, let me introduce a term called compressibility factor. Okay, that is, from this equation, that is PV is equal to mu RT, we can write PV by RT, okay, PV by mu RT is equal to Z. Okay, PV by mu RT is equal to Z, where Z is called as the compressibility factor. So, we are going to plot a graph between the compressibility factor and pressure of different gases. Okay. So, here is the graph. On the y-axis, on this y-axis, we are considering compressibility factor Z. Okay. And on this x-axis, we are considering pressure in ATM. Clear? Now, see here, your compressibility factor Z is equal to 1 for ideal gas, this violet line, okay, that represents the ideal gas. So, for ideal gas, your Z will be equal to 1, okay. Now, for some gases like nitrogen or helium, their compressibility factor is greater than 1, okay. Also, you can see some other gases like H2, CO2 as well as CH4. Initially, that is under low pressure, as you can see, when the pressure is too low, okay, their Z value is less than 1, right? Compressibility factor is less than 1. As you are increasing the pressure, they show ideal gas behavior at some point, right? At a particular temperature and pressure, these real gases will change their behavior and reach the ideal gas behavior. Okay, when we again increase the pressure, again change the pressure and temperature, then their compressibility factor become greater than 1. Okay, you don't have to by heart this graph, okay. You just have to understand some important points like if the compressibility factor is 1, then that represents ideal gas. Okay. Then the real gases have compressibility factor greater than 1 as well as the compressibility factor less than 1. Okay. And some real gases will show ideal gas behavior at certain condition of temperature and pressure. Okay. Usually real gases show ideal gas behavior at low pressure and high temperature. Okay. Then what is the equation of state for these real gases? What is mean by equation of state? Equation of state means it is the equation that connects the state variables. Okay, state variables means the variables like pressure, temperature, volume are called as state variables. Okay, the equation of state, that is an equation connecting these state variables for ideal gas is PV is equal to mu RT. Similarly, for real gases, what is the equation of state? It is called as van der Waals equation. Okay, van der Waals equation. For deriving this van der Waals equation, we consider two types of correction. That is volume correction as well as pressure correction. Okay. Why do we have such correction? It is because we have kinetic theory of ideal gases. Okay. We will be learning about kinetic theory of ideal gases in the next lecture. Okay. So, according to the kinetic theory of ideal gases, we consider the molecules have point masses. Okay. That is volume of the gas molecule as negligible. But in real gases, in reality, these gas molecules are having certain amount of volume, right? So, the available space for free movement of these gas molecules inside a gas will be less compared to ideal gas. Hence, we have a volume correction that is V minus NV. Okay. Similarly, in pressure correction, usually, according to the assumption of kinetic theory of ideal gas, we neglect the intermolecular force of attraction or repulsion between gas molecules. But in reality, these gas molecules are having certain amount of interaction in between them. There is intermolecular force. Okay. Hence, the pressure will be less compared to ideal gas. Okay. That is the pressure correction. That is P plus AN square by V, where V is the volume. A as well as B in the volume correction are constant. N is number of moles. Okay. So, we can write the van der Waals equation as P plus AN square by V square into V minus NP is equal to nRT. I have told you that for number of moles you can consider N or mu. Okay. So, this equation, this is van der Waals equation. Okay. You may be already familiar with this equation in chemistry as well as in unit and measurement. There is a question, right? Find the unit and dimension of A and B, the constants in this equation. Okay. So, try to do it. Okay. Now, we will learn about gas laws. Okay. These laws are already familiar for you. Okay. Which are the gas law? Boyle's law, Charles' law, Avogadro's law, Gay-Lussac's law, right? Then Dalton's law of partial pressure, Graham's law of diffusion. So, these are the gas laws that we are going to discuss. And out of that, first we will see what is Boyle's law. Okay. We know that PV is equal to mu RT, right? Here, if you consider the mu as well as the T, that is temperature, as constant, okay, then your mu is constant, T, that is temperature, is constant, R is already a constant, that is universal gas constant, right? So that your PV will be equal to a constant, right? PV will be equal to a constant. Okay. This PV is equal to a constant. This is Boyle's law. Or from here you can write your pressure is inversely proportional to volume, right? Take this V to the right hand side. So P is inversely proportional to volume, which means if volume increases, then the pressure will decrease. If the volume decreases, then the pressure will increase. Okay, that's basically Boyle's law. Also, for doing problems, if PV is a constant, okay, then P1 V1 will be equal to P2 V2 will be equal to P3 V3, like that. Okay, so this is also something you can note. P1 V1 will be equal to P2 V2. Okay. Now, how can you define Boyle's law? Yes, keeping the temperature and number of moles as constant, pressure of an ideal gas is inversely proportional to the volume. Okay, that's how you will define Boyle's law. Now, let's see the graphical representation of Boyle's law. Okay. There are 5 graphs here, right? So let's explain one by one. Let's see what is the A graph. Okay, in A graph, we know that pressure is inversely proportional to volume. So as volume increases, the pressure should decrease, right? Okay, as volume increases, the pressure should decrease. Okay, you have to remember, wherever a quantity is inversely proportional, the graph will be of this shape. Okay, you have to remember this. Now, in your B graph, you know that your pressure into volume is a constant, right? Is constant. Pressure into volume is constant, right? So, if you increase the pressure, as you can see on the x-axis, it is pressure, right? So, if you increase the pressure, should pressure into volume change? No. Pressure into volume, which is on the y-axis, should not change if you increase the pressure, because pressure into volume is a constant according to Boyle's law. Hence, the graph will be parallel to x-axis. Okay, graph will be parallel to x-axis. Clear? Now, let's see the C graph. Okay. In C graph, again, on the y-axis, it is pressure into volume, which is a constant. Okay. And if you increase the volume, should pressure into volume change? No. The pressure into volume is a constant. Hence, the graph will be parallel to x-axis. Clear? Now, let's discuss the D graph. Okay. Now, the D graph is very simple. You can say this. You can say this one, that is pressure is proportional to 1 by V, right? Pressure is directly proportional to 1 by V. Either you can say pressure is inversely proportional to volume, or pressure is directly proportional to 1 by V, right? So, as 1 by V increases, the pressure should increase, right? So, that is this graph. As your 1 by V increases, the pressure will increase. Okay. So, the graph will be like this. As 1 by V increases, the pressure will increase. Okay. Similarly, You have pressure proportional to 1 by V, right? You take this volume to the left side. So PV proportional to 1. You take volume, you take your, just a minute. You take pressure to the right side, so that volume proportional to 1 by P, right? Volume proportional to 1 by P. See here, in the E, okay, as 1 by P increases, the volume will increase, right? The volume should increase, okay, because volume is directly proportional to 1 by P. So these are the 5 graphs related to Boyle's law. Isn't it easy? Yes, it is easy, right? Now let's see what is Charles' law. Okay. So we will learn Charles' law. Okay. We know that PV is equal to mu RT, right? If you keep your number of moles as well as pressure as constant, okay, then the volume will be directly proportional to temperature, okay, which means that if you increase the volume, then the temperature will increase. If you decrease the volume, the temperature will decrease, right? So from here you can write V by T is equal to a constant, right? V by T is equal to a constant. Also, for doing questions, you can remember V1 by T1 will be equal to V2 by T2 will be equal to V3 by T3 will be equal to like that, etc. Okay. So, this is also important. Okay. So, how can you give the statement of Charles' law? Keeping the pressure and number of moles as constant, the volume of a gas is directly proportional to its temperature. Okay. Also, you have to note a very important equation. That is, if the pressure remains constant, then you know that as you increase the temperature, the volume will increase. If you decrease the temperature, the volume will decrease. Okay. If you increase or decrease the temperature by 1 degree Celsius, then the volume will increase or decrease correspondingly as 1 by 273.15 of its initial volume. Okay. Then, if you increase the temperature by T degrees Celsius, okay, if you increase or decrease the temperature by T degrees Celsius, then what is the corresponding volume? There is an important equation, that is, the volume at T degrees Celsius, that is Vt, is equal to V0, that is volume at 0 degrees Celsius. Okay, this is volume at 0 degrees Celsius into 1 plus 1 by 273.15 into T. Okay, where this T will be temperature. Okay, temperature in degrees Celsius. Okay, this concept can be given as a graph, can be represented as a graph. Okay, as you can see here, at minus 273.15 degrees Celsius, your volume is 0. Okay, just consider your volume as 0. Okay, then as you increase the temperature, your volume will increase. Okay, at 0 degrees Celsius, your volume is represented as V0. Okay, then as again the temperature increases, the volume is increasing. Clear? So as temperature increases, the volume is increasing. Okay, I hope it is clear to you. It will be more clear while we are doing some numerical questions based on these formulas. Okay, now let's see the graphical representation of Charles' law. Okay. These are the graphs related to Charles' law. Let's see the A graph. Okay. We know as volume is proportional to temperature, as temperature increases, the volume should increase. So the graph will be like this. Okay, as temperature increases, the volume is increasing. Okay. Now, what about the next graph? The next graph is, we know that as volume is proportional to temperature, okay, V by T is a constant, right? I'll write here, okay? I'll write here, then it will be more clear. Okay, I'll write here. Your volume is proportional to temperature, alright? So that V into 1 by T is a constant, right? Is constant. Okay. Which means that if volume increases, your 1 by T should decrease. If your 1 by T increases, the volume should decrease. Right? You didn't understand? Then think like this. You have 2 into 4, which is 8. Alright? If you increase the 2 and make it 4, then your 4 should decrease to 2, so that it becomes again 8. That is, in general, if you have A into B is constant, let's put K. K is constant. A into B is constant. Then as your A increases, the B should decrease. Okay. As your A decreases, the B should increase. That concept is represented in this B graph. Okay. So as your temperature increases, the 1 by V should decrease. Okay. So that's the graph. That's the basic logic. As temperature increases, the 1 by V should decrease. Or in the next graph, that is in the C graph, also you can see, if 1 by T increases, your volume should decrease, right? If 1 by T increases, the volume should decrease, right? This is just based on this concept. Okay. Now, what about the D graph? In D graph, you know that your V by T is a constant, right? V by T is a constant. Okay. So the V by T should not change. The V by T should not change if you change the temperature or if you change 1 by T. Okay. So you change T or 1 by T, your V by T remains a constant. So that is parallel to x-axis. Clear? Also, in the E graph, you know that V by T is a constant. Hence, if you change the volume V or 1 by V, your V by T should remain a constant, that is parallel to x-axis. Is these things are clear to you? Okay. So these 5 graphs are simple. If you know the equation, just think mathematically. Okay, you will understand that. Now, let's see the next law. The next law is Gay-Lussac's law, which is also called as pressure law. Okay. So what is it? You know that your PV is mu RT. Right? If you keep mu as well as volume as constant, okay, then you can tell that your pressure is proportional to temperature, right? Which means that if you increase the temperature, the pressure will increase. If you decrease the temperature, the pressure will decrease. Okay. So, P by T remains a constant, right? Your P by T will remains a constant. Hence, we can also tell that your P1 by T1 should be equal to P2 by T2 should be equal to P3 by T3, etc. Right? Okay. So this is also important for doing numerical questions. So how can you define Gay-Lussac's law? The law can be defined as volume and number of moles remains constant, the pressure of an ideal gas is directly proportional to its temperature. Alright? Then you can note something very important, that is, as volume remains constant, if you increase the temperature, then the pressure will increase. If you decrease the temperature, then the pressure will decrease. So if you increase or decrease the temperature by 1 degree Celsius, then the pressure will increase or decrease correspondingly as 1 by 273.15. Okay. So what will be the pressure if you increase the temperature by T degree Celsius? Okay, if you increase or decrease the temperature by T degree Celsius, then what will be the increase or decrease in the pressure? Okay, then the equation is PT is equal to P0 into 1 plus 1 by 273.15 into T. Okay, where P0 is pressure at 0 degree Celsius. Okay, and T is the temperature. Okay, T is the temperature in degree Celsius. Okay, now this can be represented as a graph. Okay, at minus 273.15, the pressure can be considered as 0. If you increase the temperature, then the pressure will increase. At 0 degree Celsius, we can consider the pressure to be P0. Okay. Then as temperature increases, the pressure is increasing. Clear? Then the equation to find the pressure at T degree Celsius is this one. Clear? So that is the basic idea behind this graph, and this is an important equation too. Clear? Okay. Now let's see what is the graph related to Gay-Lussac's law. Okay. These are the graphs. So I'll explain you these graphs. Okay. What about the A graph? In the A graph, we know that pressure is proportional to temperature. So as the temperature increases, the pressure should increase. Clear? Now what about the B graph? The B graph is, you know that your P by T is constant. Alright? Is constant. So your P by T should not change if you change the temperature or if you change 1 by T. Okay, that is the reciprocal of temperature. The P by T should remain a constant that is parallel to x-axis. Clear? Similarly, in the C graph also, your P by T is a constant. Hence, the P by T should not change if you change the pressure or if you change 1 by P. Clear? Now what about the D graph? The D graph is, you know that your P is proportional to T. So you can tell that P into 1 by T should remains a constant. Alright? That is, if your P increases, then your 1 by T should decrease. If your P decreases, then your 1 by T should increase. Alright? You know that idea. I have already discussed in the previous graph discussion also. Alright? So if P increases, your 1 by T should decrease. If P decreases, your 1 by T should increase. Then only their product will remain a constant. Similarly, if you need, you can take this P to the right side. So that T into 1 by P will remain a constant. Right? Again, it is the same thing. If the temperature increases, 1 by P should decrease. If the temperature decreases, then the 1 by P should increase. Right? So that their product will remain a constant. Okay, you get the logic. So that two logic is represented in this D graph and D graph. If temperature increases, the 1 by P should decrease. If the 1 by T increases, then the pressure should decrease. Clear? I hope you get the idea. Okay. Now, let's see what is meant by Avogadro's law. Okay. The Avogadro law is already familiar to you, right? That is equal volume of two gases. There are two gases. Suppose in container A, there is a gas. In container B, there is another gas. Okay. And if these two gases have equal volume and are under same condition of temperature and pressure, that is pressure of A gas is equal to pressure of B gas, temperature of A gas is equal to temperature of B gas, then the number of molecules in both the gases will be equal. Okay, that is Avogadro's law. It is very simple. Okay, so we can say that the N1 will be equal to N2. Clear? Now let's see what is meant by Graham's law of diffusion. Okay, that is when two gases at same pressure and temperature are allowed to diffuse into each other. What is meant by diffusion? Usually the term diffusion means the flow from high concentration to low concentration. So if you allow two different gases, okay, under similar condition of temperature and pressure to diffuse into each other, then the rate of the diffusion will be inversely proportional to square root of density of those gases. Okay, that is, you can write the equation as R1 by R2, where R1 is the rate of diffusion of the first gas, R2 is the rate of diffusion of the second gas. So R1 by R2 will be equal to square root of rho 2 by square root of rho 1. Okay, that is the density. Also, it is equal to square root of M2 by square root of M1. What is this capital M? This is the molecular weight of the gas. Okay, molecular weight of the gas. Okay, so this is the equation. Also, if V volume of gas is diffusing, okay, I'll write here V volume of gas diffuse in time t, okay, then the rate of diffusion is given as V by T, okay, V by T. So if there are two gases, then R1 by R2 will be equal to V1 by V2 into T2 by T1, right? So these are some of the equations related to Graham's law of diffusion. Okay. Now you may have heard about effusion, right? Effusion is something you are learning in chemistry. Okay. Here we have to learn diffusion. Okay. Now we are going to learn the last and final gas law, that is Dalton's law of partial pressure. This is familiar to you, right? So let's take an example, okay, so that we can learn it in a very simple way. If you have a gas in the first vessel, then the pressure exerted by this gas can be marked as P1, right, which is called as partial pressure. Okay, and now you have another gas whose partial pressure is P2. Then if you combine these two, gases. Okay, these two gases are non-reacting gases. So if you combine these two gases, then what is the pressure exerted? What is the total pressure? Okay, then the total pressure can be given as P1 plus P2. Okay, which is the sum of the pressure due to individual gases. That is the partial pressure. Okay, so if there is N non-reacting gases in a vessel, then the total pressure will be sum of the pressure due to individual gas. That is their partial pressure. So we can write, generally we can write P total is equal to P1 plus P2 plus P3 plus etc. plus Pn. Right? Okay. Now let's write it here. P total is equal to P1 plus P2 plus etc. plus Pn. From ideal gas equation, you know that the pressure into volume is mu RT, right? Mu RT, right? So the pressure can be mu RT by V. Okay, so using this equation of pressure, you can write your P total as mu total into RT by V is equal to mu 1 RT by V plus mu 2 RT by V plus etc. plus mu n RT by V. Clear? So now let me ask you something. What will be P1 by P total? What will be P1 by P total? The P1 by P total will be equal to mu 1 RT by V whole divided by sum of these things, right? That is mu 1 RT by V plus mu 2 RT by V plus etc. plus mu n RT by V. Isn't it? So you cut the common terms RTV, 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 right? So the remaining is mu 1 by mu 1 plus mu 2 plus etc. plus mu n, or which is mu 1 by mu total, right? This is called as Chi, that is mole fraction. It's called as mole fraction. Okay, so from here we can tell a very important equation, that is partial pressure of any gas Pi is equal to mole fraction of that gas, that is Chi into total pressure. Clear? I hope you get the idea. From here and from this last Chi, that is the mole fraction, we can write the partial pressure of any gas I, Pi, is equal to the mole fraction of the gas multiplied by the total pressure in that gaseous mixture. Clear? So these are the important concepts that you need to know about the behavior of gases as well as gas laws. In the upcoming lecture, we will be practicing many questions related to these concepts. Okay. Also, now you may have understood, right, what is the nature of this chapter. It is not like mechanics. This is theoretical chapter. Okay. Hence, you may feel bored. Okay. Because most concepts are already familiar for you. Okay. So, what do you have to do? If you feel sleepy, okay, sometimes there is a possibility that you feel sleepy, right? So, you put the video to 1.5x and watch it very fast so that you don't feel sleepy. Okay. I hope you understand that. Okay. So, why did I tell this at the last moment is, now you have understood the nature of the chapter. It is theoretical. Okay. So, see you all. Bye-bye. you.